Okay, now ideally, well, we have these three equations to solve. Now, ideally, having done the homework, you would come in here knowing everything you need to solve these. Of course, this is a kinder, gentler course where I give you hints. Okay, in the pre-calculus course, you just got to come in knowing this, which is why we're doing it in this support course. Okay, but ideally, since you did have the homework on this stuff, you would ideally know this. I'm not getting on you for not knowing it, because again, this is a kinder, gentle course. Okay, but I'm trying to get you ready for what you're going to see probably within a week or two in your pre-calculus course, if you haven't already seen it. Because in my pre-calculus course, we're already into this stuff, so we're just about a day or two ahead. Okay, it's very difficult to stay ahead in this course, but that's really the way I've constructed it. Okay, and I'm thinking that that's probably the best way to do it, but we'll see. Okay, so anyhow, here are the three equations. And here's the key to solving the equations. It's this equivalence between logarithms and exponential form. Okay, now we've been over why you have that equivalence, because of the inverse function relationships and stuff. Ideally, you understand that, but that's a stretch for most pre-calculus students. Okay. So if you don't totally understand why, at least understand that this is the rule, and it does come from what happens if you reverse the columns in a table to get an inverse function. It's an inverse function property. But there it is. Now, the mechanics of solving these things. Okay, let's say B is 5. So we've got 5 to the x equals C, which let's say is 11. Okay. Now, form is B to the A equals C. It's clear you have some number to a power equals some other number. Forms B to the A equals C, where B is what? Well, B is the thing that's raised to the power. B is the base of your exponential expression here. It's 5. A is the exponent, and the exponent here is x. And C is what's on the other side of the equal sign, and that's 11. So it's easy to identify A, B, and C if your equation is in this form. I'll say so. Log base B, which is 5, of C, which is 11, equals A, which is x. After a while, you can look at these and see the base of your exponential becomes the base of your log. And what's on this side goes in here, and it goes over here. But right now, you want to do this. So this is with these numbers, this equation is this form. So we translated this to this so that x equals log of 11 over log of 5. Now, I didn't write this rule for you, because really you should by now understand this rule, or at least know this rule. But the rule is written. Log base b of whatever is a log of whatever over log of b. Could be from a calculator. You could estimate it from a graph. On a graph of log base 5. I'm not likely to do that, or graph of log base 2. Okay, log base 2 of 11 is something you could actually estimate if you just extend your basic graph. But I'm not going to require you to do that. Not going to require anybody to do that in my pre-calculus course, but just indicating that if you have that graph, you can actually make a pretty decent estimate of what this log would be and what this log would be. Okay. Up to the let's say you got 2 to the x minus 7 equals 15. This is a form. The form b to the x, b to the a equals c equal to a equal to x minus 7, because a is the exponent. B is the base, that's 2. A is the exponent, that's x minus 7. And c equals 15. So this becomes, again, it helps to write it down. If you're not writing down these steps in a coherent fashion, you're not seeing it as coherently as would greatly benefit you, okay? Follow the form that I'm doing here and then adapt it to your own style. But for right now, write down these steps to remind yourself and reinforce what it is you're doing, because you come back to it 2 days later and you kind of forget the details and you start writing stuff down. It might be right, it might be wrong. If you are used to writing out the details, you're more likely to know it when you need it. Okay, well, we have 2 to the x minus 7 equals 15. We've identified A, B, and C, and that's going to put this into the form log base of C equals A, which over here then would be log to the base 2, because B is 2, of C, which is 15, and that equals x minus 7. Well, that's easy to solve. Add 7 to both sides. You get this, and that gives you then kind of reversing sides. X equals log base 2 of 15 plus 7. You don't combine the 15 and the 7. The 15 is all bound up in log base 2. You don't know what that number is, but you're certainly not going to be able to add it to 7 until you figure out this number. Of course, this number is easy to figure out using this. You get log 15 over log of 2 plus 7. You take out your calculator. And log base 15, log base 2 of 15 is a little less than 4, because 2 to the 4th is 16. Wouldn't hurt to be able to think through that, but right now, just understand your calculator is going to get that for you, okay? And you can refine your understanding a little more in pre-calculus. All right. Now, third equation is log base 2 of let's say it's 6x minus 9 equals, those would not be your typical D and B, because D is always bigger than B, but it doesn't matter. The procedure is the same. Okay, right up. This is a log base B of C equals A. With B equals 2, because it's log base B, log base 2. Just going in order. C, the thing you're taking the log of, is your 6x minus 9. And A equals 14. A being the thing on the other side of the equal sign. So this is a form, this is B to the A equals C, which gives you 2 B to the 14th. That's kind of a big number. Okay. So 17,000, something like that. Yeah. 16,000. 786, I think, something like that. Okay, 2 to the 14th equals, though, your 6x minus 5. Translating this form to this form. Very, very simple process if you know these equivalences. And then we easily solve. Okay, we get 2 to the 14th plus 9 equals 6x minus 9 plus 9. So 2 to the 14th plus 9 equals 6x. So that 2 to the 14th plus 9 over 6 equals 6x over 6. So that x equals 2 to the 14th plus 9 divided by 6. Now let's see. I got this right. 1024, 2048, 40, 96. And it's 192. It's 8,192. So it's 16,284. 16,384. And of course, you should use your calculator, see if I did my arithmetic correctly. And it's 96, not 92. So that ought to be 16,392 there. 16,401 over 6. 16,401 turns out to be a multiple of 3. So that's just doing the arithmetic. That's 5,467 over 6. And that's not over 2. Yeah, you can get the decimal equivalent. Now you do your calculator, you're probably just going to get a decimal equivalent. That's going to be something 0.5. There you have it. Okay. Now that's how you solve these things. If you know that much of the mechanics, then you're going to find it much easier when you encounter these equations in pre-calculus. And when you encounter the meanings of these equations, like for compound interest and stuff like that, which I believe I kind of talked about a little bit in here, but that might have been in pre-calculus, I don't remember. One more equation, a typical equation you might get, and I probably did one like this. Let's see some of this stuff. This is all, yeah, it's still visible. Okay, so if you have like you invest $1,000 at 4% annual interest compounded annually. You want to know how long it's going to take to get $5,000? There's your equation. Solve that equation easily. But it isn't in one of these forms yet. You see that it can be put into one of these forms rather easily if you just divide. Yeah, the reason it's not in one of these forms, you do have a b to the a and a c, but you've also got something out in front of your b to the a. Okay, so you're going to want b to be 1.04. You're going to want a to be t, and you're going to want c to be $5,000, but not really, because you still have this $1,000 here in your way. So to get that in the form b to the a equals c, you divide by 1,000. $1,000 times 1.04 to the t divided by $1,000 equals $5,000 divided by $1,000. So that 1.04 to the t equals 5. And now you're home free. You can solve that. I'm not going to do the rest of the solution. Well, I'll just write it out. After a few steps, I'll indicate by an ellipsis here, 3 dots. T equals log 5 divided by the log of 1.04. Okay. Now, t is going to be 1836, somewhere around 40. Using the rule of 7, which is kind of convenient. That's a 40 with a question mark. You can check it out on your calculator. Now I calculate that. Well, you know, I thought this was all visible. Unfortunately, the angle I need the computer screen, I have to walk up and see things, is not the angle I need to see it from back here. So I can't see the computer screen as well as I ought to. So when I checked it, thought I saw it, but I didn't. Okay, anyway. Again, this equation is real easy to solve. Divide by 1,000, and you get this, and that's just a correct example of your basic form. And you get this. And what I was going to say is the doubling time at 4%, you have this thing called the rule of 72. You divide 72 by your percent, here your 4%, and you get 18. And that's about how long it takes this thing to double. So after 18 years, this is annual compounding, which it probably is, you'll have $2,000. After another 18 years, you'll double again, you'll have $4,000. Then you got to get up to 5,000. Well, if you were to double again, you'd be at 8,000. Well, another 18 years, you'd be at 8,000. That'd be 54 years. So somewhere between 36 and 54 years, you're going to hit 5,000. 5,000 is closer to 4,000 than it is to 8,000. So I say it's in the low 40s somewhere. So I just said approximately 40. It's a little more than that, 42 maybe. Okay, but your calculator will tell you. But the rule of 72, which I believe you see in your materials, is kind of a convenient way to think about how long it takes something to double. As long as the interest rate is pretty low. That works. Okay. I just hit the wrong button. Okay. The hearing threshold is, I'll just write it. Ten to the negative 12 watts per square centimeter. Now, what's a watt? Well, you have 100-watt light bulbs. Okay. So you run through an old incandescent bulb 100 watts, or run about 20 watts through an LED. Then you get a certain amount of light. Okay. You run 10 watts through your refrigerator. 10 watts. I'm sorry, you run 1,000 watts through your refrigerator, 10 amps. 1,000 watts through your refrigerator and cools things off inside. Okay. You run 1,500 watts through a space heater in a standard wall socket. Okay. That's about as much as you want to run through that standard wall socket before you start overheating the circuit and blow fuses. Okay. That 1,500 watts, and that'll heat your room. It's not too cold outside. Okay. Now, this is 10 to the negative 12 watts. Okay. What we're talking about with your electricity is the energy that you have to get from your power station and your circuit in order to run those things. Okay. So you get up to close to 2,000 watts if you're using number 12 wire in your circuits and a 20 amp breaker. So you get on the order of thousands of watts. Okay. We probably have the order of 1,000 watts in the fluorescent bulbs in this room. This is 10 to the negative 12th watts, which is a trillionth of a watt. Okay. It takes a trillion of these to make a watt. And that's the energy that falls on your ear per square centimeter. Now, square centimeter is about roughly the area of your ear canal. Your ear is constructed in such a way that you really probably pull in close to maybe 10 square centimeters worth of energy and get that to your eardrum, okay? Cause your eardrum to vibrate. So maybe you get 10 trillionths of a watt, okay? At the hearing threshold. Now, I can't hear at the hearing threshold, and neither can you. That's something very unlikely that you can, because your hearing deteriorates. Okay, and mine's deteriorates. I've got hearing aids. Your hearing deteriorates from birth, basically, because sound wears on your hearing mechanism, damages the little hairs that vibrate. So, okay, this is just a little bit. A trillionth isn't much. Okay, a thousandth of this is about this. What's a thousandth of this? It's invisible. Okay, it's a millionth of this. Okay, and then you take a thousandth of this, whatever tiny thing that is, and take a millionth of that, and you've got a trillionth. Okay, so you've got 1 watt. That's a thousandth of a watt. A thousandth of that is a millionth of a watt. A thousandth of that is a billionth of a watt, and a thousandth of that is a trillionth of a watt. Now you say, what? Okay. That's a little hard to grasp. A trillion is a difficult number to grasp. A billion you can grasp. Let's say you've got ground pepper. Peppercorn, the pepper grains are real small, right? So you can line up 1,000 of those. Okay, maybe in that distance, okay? And that'd be a line of 1,000. Now you do 1,000 lines of 1,000, 1,000 lines this way, you get 1,000 lines this way. So you cover maybe something like this with pepper grains, and you'd have 1,000, which is 1,000,000, okay? Then you make layers this high, and you got 1,000,000,000. So you kind of visualize 1,000,000,000. You visualize filling a container this size with pepper, right? You maybe have 1,000,000,000, depends how finely you ground it is. And you have different ways of grinding it. And if you want 1,000,000,000,000, then you got to get 1,000 of these, which you can get by lining up 10 of them this way, 10 of them this way, and 10 of them this way. So if we had a container a little bigger than that, okay, wide and long and high, okay, maybe about this high and acute, right? That'd be 1,000,000,000,000, okay? Okay, well, to give you a sense, because these numbers are really big and it's hard to grasp them, but it's easy to grasp their logarithms. And that's the whole point of my little story, okay? So, going to the hearing threshold thing, you got 1,000,000,000th of a watt per centimeter. It's not much energy. And a healthy newborn's ears can hear that. It's way less than the distant rustle of leaves in a gentle breeze, okay, or whatever. The tiniest whisper you can imagine. Now, if you got a dog, it sounds like you're yelling because they can hear anything. Okay. Now, about 1 watt per square centimeter. So it's 1,000,000,000,000 times as loud as the tiniest sound you could hear when you were born, assuming your ears were healthy when you were born, okay? I kind of think mine were. I think I've just got normal aging, which gives me moderate hearing loss. You got to talk a little louder, maybe a little slower for me to understand it if I don't have my hearing aids in. So this is 1,000,000,000 times as much as this. This is like one little grain of pepper, one tiny grain of pepper, okay? Out of a big old huge box of pepper, okay? Okay, we measure sounds not in energy per square centimeter, energy density information. To get a handle on it, okay, I'm going to use a letter This is the sound intensity. I call this I sub 0 or I naught. This is I max. And incidentally, just another little story. We took our governor's school class a couple of summers ago down to the Kennedy Space Center, Cape Canaveral, whatever. The big space center. And the guy told us a story, said, when one of these rockets launches, if you're within a quarter mile, the sound will kill you. Okay? Now, how does the sound kill you? It doesn't blow you apart, although an intense enough sound could. And maybe there are limits to the physics there. And I don't want to think through that. I have to think pretty hard. Take me a while, if I can even do it. Within a quarter mile, or something like that, the sound will kill you. Within a mile, if you're within a mile of the thing, the snakes and alligators will kill you. Okay? Because they get all riled up. This thing is really loud. I don't know if you've ever seen a rocket launch. I haven't. They'd probably pass out from excitement. I think rockets are really neat. Okay. Yeah, just the power and understanding things about the power and stuff like that. But how does the sound kill you? Well, sound is pressure waves, pressure oscillating back and forth. Okay. Now, if the pressure oscillates back and forth out here, it's going to oscillate back and forth in my lungs. And if the pressure oscillates too much in my lungs, it's going to destroy them. That's what kills you. Now, I conjecture that. I didn't ask them. Didn't want to distract them with facts. No, with questions that not everybody would understand. But I'm pretty sure that's what happens in an explosion. If you're close enough, of course, the explosion will blow you apart or traumatize you in some other way. But at a little more distance, even if the shrapnel and the shock wave doesn't destroy you, the pressure wave will destroy your lungs. That's the most vulnerable part in an explosion. I would other part, assuming you escape the shrapnel and the trauma, the other trauma of the shock wave. Of course, the shock wave also destroys your lungs, but kills you more or less instantly if you're close enough. Okay. Anyhow, we define decibels. If your lungs are destroyed, it takes a little while. Okay, not a whole lot because you're not getting much air, and you kind of drown in your own blood. Okay, you define decibels as follows. Writing 10 and log at the same time, that's not really a good way to write. It's 10 times the log log. It's a key on your calculator, and it's the inverse to the 10 to the x function. For I is the intensity of a sound. Okay. Well, I'm going to ask you to calculate this. Calculate your decibels if I equals I max. Now, I've already told you what I max is, and I've told you what I naught is, right? You're just going to plug this and this in for I and I naught, and then do the arithmetic. Okay, so I'm going to go ahead and do this because most of you are. Now, what I'm not saying is I'm not really seeing a good form in most of your solutions. Some are better than others, some are bad, but mostly the form isn't real good. And if the form isn't real good, as I say, one disadvantage is you're not reinforcing the relationships, okay? You're also going to be more prone to make errors. So what I mean by a good form on this would be something like this. Okay, so you say, first right, dv equals log base 10 of I over I naught. That equals log base 10 of this problem of I max over I naught. And it wouldn't be bad to remind yourself that what you're doing is I max over I naught, because your goal here is not just to get the right answer. Your goal is to understand what's going on. Because if you understand it, then you remember what to do much better. So this is log to the base 10 of 1 watt per square centimeter divided by 10 to the negative 12 watts per square centimeter. Now, watts per square centimeter divided by watts per square centimeter is just essentially 1. But if you want to write this out, so you see that this divides this and kind of goes away, kind of cancels. I don't like calculation. Think of it as equal to 1, so you don't have to write it anymore in the product. So, okay, so this is log to the base 10 of 1 over 10 to the negative 12. Now, what's 1 over 10 to the negative 12? Well, you know, from the very beginning of the course, we've tried to emphasize rules for exponents. You need to be more on top of the rules for exponents than most pre-calculus students are. Because again, it's something people stumble over that should have been covered much better and reinforced much better in intermediate algebra courses. Still, to say that your rule is, remember that a to the negative b is 1 over a to the b, right? Okay, well, you have a 1 over a to the b here, with b equal to what? Negative 12, right? Okay, well, 1 over 10 to the negative 12 by this rule is 10 to the 12. Okay, by a lot of stuff that you ideally would have done a lot more of with exponents than your prerequisite courses. Get this. Okay, I'm not going to belabor this, but it's a simple application of this rule with b equal to negative 12. I'll write it on here. Yeah. If b is negative 12, then we got a negative 12 here, and a negative b, which is negative 12. That's how we get 10 to the negative 12th in the denominator and 10 to the 12th in the numerator. Other ways of understanding, well, there are other ways. I want to kind of concentrate on the logarithmic aspect of this. Okay, so when I say write down the equation, write down the details, you want to write down the correct details. Like I did. Fortunately, I can fix it. Very easy. I didn't put the 10 in there. There's 10. Okay. Well, what's the base 10 log of 10 to the 12th? We can say log base 10 of 10 to the 12th equals x, if and only if ten to the x equals 10 to the 12th. Just using the rule that we started class with. But log base 10 of 10 to the 12th equals 12, which we can understand immediately from the inverse function relationship as well. You're going to see this in your materials. In any case, log base 10 of 10 to the 12th is 120, and you don't need your calculator to do that. Your calculator would tell you that. But in this case, you don't really need it. Worth understanding. Okay. Again, I write out every step, then I understand it better. Okay? So it doesn't hurt to imitate what you see, but try to then understand why what you're doing is the reasonable thing to do. And if you just start by plugging in these two numbers, the rest of it should pretty well follow. At some point, you see what to do. And then you go back and you think about what you started with and think about why this works. Okay. So what's the value of I if your decibel level is 74? Now 74 is a little louder than I'm talking. If I talk at 74 decibels, you're going to think I'm kind of yelling. Okay. I can talk louder than that, but then I'm really yelling. Okay. I've never actually measured it. I'm sure you talk over 74. How do you answer this question? Well, you start with the equation. You start with the definition. If you write you know, 10 is written a lot like LO. So I'm wondering if that's what's going on in my feeble brain here. I might want to write LOG instead of the 10. If I focus on the LOG, the 10 just kind of goes along. Okay. There is our definition of decibel, right? Now, what term here or terms can we substitute for in this situation? So let's talk about that, because we don't have time to ask you to work on it. Okay, so we know dB, it's 74, so instead of dB, we write 74. I want to write that as an O rather than a 0. Stop it. Okay, now that's 10 log of I over 10 to the negative 12th watts per square centimeter. Now I got to solve that for I. Well, at this point, I've got to know how to translate logarithmic form to exponential form. This is well, it isn't yet. To solve for I want this in the form of a log V of C equals A. Not yet in this form, but it's going to be when I divide both sides by 10. Now, out of time, so I'm going to abbreviate this. We divide both sides by 10 and put this over here to get log of I over 10 to the minus 12 watts per square centimeter equals 7.4. It's real easy to divide by 10. We don't need a calculator to do that. Okay. So translating this to exponential form, remember that log means log to the base 10. And if you want, you can put the log base 10 here. So you know that I over 10 to the minus 12 watts per square centimeter equals 10 to the 7.4. Then we multiply both sides by this denominator. By 10 to 7.4. This stage, all you got to do is plug this into your calculator, and you're going to get the value of I. Now 10 to the 7th is, well, 10 to the 7th and 10 to the 0.4 is about 4, roughly, okay? No, it's about more than 2. 10 to the 0.5 is about 3.1 square root of 10. If you look at a table, it's pretty straightforward. It's more than 2. Okay, well, whatever it is, your calculator is going to tell you. And you're going to get something like 2 point something times 10 to the negative 5th watts per square centimeter. Okay. But your calculator is going to tell you, and you're going to have it. So this is just an instance of how you solve a logarithmic equation once you put your numbers in.